So today actually is possibly historically the most fun bit of the whole course, because there is one real hero to the story that we can talk about a little bit, Michael Faraday. I'm sure you've read his biography already. You know absolutely everything about him. Maybe not. If you haven't, then it's really quite worthwhile to do, because he was a very lively, colorful, productive, sociable, actually really all-rounded individual. He was not a theorist. He was really very much a hands-on person, and he was just fumbling around with stuff continuously, but in a very organized, systematic, and brilliant fashion. So he was able to do really quite a number of experiments that proved absolutely pivotal in the development of electrodynamics. So the crucial year that we're talking about is 1831. Let me just get this. The crucial year we're talking about is 1831, when Faraday did a number of important experiments. Actually, they were published in 1839. You can still find the text of these things. Also, it's very, very nice to read through these texts, because you see that they contain really quite a lot of polite formulations of things, of being very deferential and whatnot. Very different from the kind of shotgun bullet style that you sometimes find today. But in that context, in 1831, actually very little was known about time-dependent phenomena. There was one thing dating from, I think it's 1820, it was Christian Ørsted, who had discovered that compass needles would be influenced by electrical fields. So essentially, in those days, there was no notion of the real connection between electrical and magnetic phenomena. And Faraday's motivation was that, at least he believed, that there would be a way for electrical phenomena to be like contagious, that the proximity of something with an electrical, he used the word induction back then, but really that was electrical induction in the sense inducing something on something else. So, so what Faraday was trying to do is really to create an electric field in a second circuit from a first separate circuit by doing something. And he believed that at first you would just need to bring those two together, and somehow there would be some transfer of effect in that. So he really did countless experiments on this. I think there are about 20 kind of really well documented, but maybe they can be summarized in about 3 different ones. The simplest one is that he started with a ring of metal material, something like this, right? And on one side, he actually wound some wire around it. And the ends of these wires here could be connected to an apparatus to measure current. So you had a little so-called galvanometer here that would move its dial if there was a current going through this. So the challenge was to kind of build a current through that thing. So of course, what Faraday tried to do is just induce the current by using another loop that was this time connected to a battery. So you'd have your 2 terminals, and you would connect the 2 ends of your thing here to your terminal. So he would have a switch, and he would kind of turn on the current here. The metal here was kind of put there to encourage the propagation of these electrical phenomena, and he was looking for a current in the second loop. Now, in the experiment, at first, he thought that this was unsuccessful, because of course, setting up the current in this one, pulling the switch and then taking a coffee and then going to look at the current in the second one here gave 0 current. However, at some point, he did notice that at the moment of turning on or turning off the current in the first loop, there would be temporarily a current induced in the second loop. So that's the first thing. So somehow it's not a steady state phenomenon, it's a transient phenomenon. It's having some time dependence to your electrical field in the first one that would induce the electrical field in the second one. So that was one thing. So another class of experiments that he did was a kind of relatively similar one, but now in a movable fashion. So you have a little battery like this. You've got the cables coming into some form of current loop. That's connected. And then you've got another loop here that you are actually connecting now to your galvanometer. So what he observed is that if he had now a static current in here, but he moved the source of that thing back and forth, then as it was moving relatively to the galvanometer's loop, then there would be an induced current. Okay, so he tried lots of different directions, lots of different configurations, but he noticed again that as you move one with respect to the other, there is a change in the reading of the galvanometer. Namely, there's a current that is seen. So that's one thing. And then he thought, well, okay, so maybe it's like not really electric, but magnetic. So then he did another type of experiment where, once again, he had his galvanometer connected to a big loop. But now what he would do is he would take a piece of a permanent magnet and he would approach it or remove it away from the loop. So he knew that there was no electricity in here, it was just magnetism. But now he realized that actually, indeed, the magnetism created by this permanent magnet, if it was made to be time dependent by relative motion of the source with respect to the loop kind of measuring this this current, then you could induce something in there. So what does it mean? If you measure a current in your galvanometer, necessarily there's an electrical field induced along this path of the loop here that is able to drive your current. Okay, so that is Faraday's conclusion. So his, the result of his big investigations is that a time-dependent magnetic field B induces an electric field E. Okay, so all these experiments are explained by this same statement, this same phenomenon here, that time dependence and magnetic fields are able to generate some electric fields for you. Okay. By the way, Faraday was doing lots of public demonstrations all the time. He's got these really famous Christmas lectures that he was doing, I think, deep into the 1850s, possibly right up until his death. Not so sure. But again, these things are very well written up. And in loads and loads of these Christmas lectures that came much after the discovery and the kind of establishment of all these things, he did like wonderful demonstrations of all these things. So you should go have a look at the literature and just see how much documentation there is about all these things. It's really quite amazing to see. Okay, so anyway, that's his big insight. Now, the way to quantify the electric field that is induced here goes as follows. So we have to introduce a notion called the electromotive force. Yeah, so to quantify, oops. Sorry about this. Excuse me. Okay, so to quantify this phenomenon, we have to introduce this this notion called the electromotive force. So to quantify, use the notion of the electromotive force. Okay, what is this? The electromotive force, we'll just write it as this curly E, is by definition the line integral of the electrical field along a closed path. So we're going to do an integral along a path, dl, and we're going to dot the electrical field in there. Okay, so we've got a certain path like this, and we're doing an integral around this of the electrical field. So how should you how should you kind of think about this? So there are many kind of ways of thinking about this. So if you have the electrical field present and you kind of manage to do an experiment where you take a unit charge and you push it around the cycle before anything changes, then the work that you're doing is this electromotive force. That's one way to think about it. A second way to think about it is, let's say you were to cut, you just do a tiny little opening in the loop here. What would occur is that there would be a potential difference between the two ends, right? And you remember our definition of the potential? The potential was really just some line integral of this electrical field, the work that you do against it. So, so by doing this imaginary slicing here, this electromotive force, yes. Nothing happened on these screens. I don't know what it is. Okay, anyway, we're back. So, so the electromotive force is really this kind of potential difference between the two places. So it's per unit charge, if you want. Maybe a kind of better, more intuitive way of thinking about it is the following. And yeah, I'm not sure it's explained in books like that, but that's just my own attempt at it. Let's imagine that you have a way of distributing charges along the whole path, and you know how much charge you've got. And this is like a mechanical gizmo that can actually move a bit and kind of capture force on it. Then if you had an electromotive force, this thing would tend to twist a bit. It would tend to develop a moment to it. That would be corresponding to the electromotive force in there. Okay, so whichever way you prefer thinking about this, then it's going to be valid. The kind of important thing is the definition here, the line integral of the electrical field along a certain path. Okay? Have you discussed the electromotive force in your first course? Not at all? Okay. Does it feel kind of intuitive? So, question.
Is there a current point?
So here we've got in your experiment, to make it simple at first, a fixed loop of something. Okay, let's say you take some copper wire and you really make a loop out of it. And now something happens in your laboratory that creates an electric field in there. So of course, if everything is static, then there is no time dependence anywhere. And we know that the curl of E in the static case is 0. Okay, so nothing happens. However, if you start juggling magnets around, you're creating time-dependent fields. And if you had, let's say, a certain loop here fixed in space, but let's say that you had a way of measuring current going through this, then you would see currents going through. And if you know the resistance of your thing, you know, if you just measure the current, you can relate that to a potential difference, if you want, between two things.
So there is an electric field moving along the direction of this wire.
If there are time-dependent magnetic fields in the vicinity of your loop, there will be an electric field induced throughout space that will be such that its integral along a closed loop will be non-zero. So you would integrate all these little DLs here, 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 and here. And at each point, you would take the dot of your DL with your electrical field. And in the end, you would get something non-zero. Okay? Time-dependent magnetic fields. And that's what we're just about to kind of quantify. Right? So maybe it's time to just do this precise statement. So the precise statement. The precise quantitative statement that comes from all these experiments on this is that the electromotive force, which is induced in a certain loop, is minus the change in time of the magnetic flux, big phi. Okay, this is the magnetic flux. Okay, where phi is by definition the integral over surface S dA of B. Okay, so you have a certain magnetic field in space. The flux going through a surface, you visualize it easily, right? So you've got your surface like this, you've got your B going all the way like this. So this is B. And the flux phi is just the integral over, so you fix a certain loop, you take a certain surface, and you just integrate the normal element of the surface dotted into your magnetic field throughout your surface here. Okay? So that's the definition of the flux. And using the definition of the flux, we make the precise statement from Faraday, okay, that the electromotive force is minus the time rate of change of the flux. Okay, so that's the we can even write it as Faraday's law. Okay, so Faraday's law takes two forms. We'll discuss it a little bit better. First form is that the closed integral over a certain path of the electrical field is equal to minus the integral over the surface defining that thing, dA, dotted into the time-dependent magnetic field, dB dt. Okay, so this is really like a fundamental equation. Faraday's law in integral form. Okay, I'll just write another couple of things and then discuss it a little bit more. So, yeah, maybe I can discuss it a little bit more right away. Okay, so first of all, the statement itself, electromotive force is minus time rate of change of flux. It's like an integral statement that you can kind of view geometrically, right? If you imagine your magnetic field as being a flow of whatever going through space, then the flux is really just the number of these things going through your surface per unit of time. Okay. Now, one very important aspect of this is that we are talking about a well-defined path, closed path. But you might object, what about the surface? Given a certain path, I can imagine an infinity of different surfaces that are circumscribed by the same path, right? I can have my path defining this flat surface here. I could imagine having another surface, which is, on the contrary, a kind of big underdome here, that would have the same boundary, but a completely different surface. Okay, so does that lead to an inconsistency in our considerations? Well, anybody has an answer to this, and mostly a reason why? No, yeah, I mean, almost perfectly correct. Yes, so the flux, well, your statement is that the flux stays constant through a surface. But yeah, so the idea is that the integrated flux through any of the surfaces circumscribed by the same ring is the same. Because how would I prove this? I would say, what's the difference between one integral and the other? Well, let me take the first integral, say on this surface here, and then plug to that surface a volume that is circumscribed by the first surface and the second surface. And in that volume, then I could integrate the divergence of B. Right? You remember the divergence theorem tells you that if you have an integral of the divergence of a vector field over an enclosed volume, then this can be written as the surface integral of your vector field dotted into the normal of the surface everywhere. Okay? We know for the magnetic field that the divergence of the magnetic field, div B, is equal to 0 everywhere, all the time. And therefore, the integral over a closed surface, or the integral over a closed volume of div B is equal to 0. Therefore, the integral of B dotted into any closed surface is always 0. Okay? But you see now, that's why these two are equal. Because if I just add this blob of volume to the first surface, I get the second surface, and these two have to be equal. So there's no inconsistency in there. Does everybody follow this this reasoning? Yeah, it's reliant on div B is equal to 0. So that's what you have. So there's no issue with the choice of the surface. Choose whichever you want, and you will be good. Okay. So so that's the first statement here. Now, of course, this integral statement here can also be given in differential form. So this is the integral form. But there's also a differential form. That comes from the fact that my loop is really an imaginary loop. I don't need a copper wire to do this. I can do this on any loop that I want. And if I use now Stokes' theorem to rewrite the left-hand side as now the integral over a surface, the A dotted into, curl of E. Okay, it's just a mathematical identity. You see, I've got now the integral over a certain surface of this vector field dotted into the surface is equal to, but this is valid for any surface S that you can imagine. And therefore, this integral equation can be glorified into a local equation that just tells you that the curl of E is equal to minus dB dt. Okay, and this is just the differential form of Faraday's law. Okay, is everybody happy with this this reasoning? There's no kind of real reason to prefer one version over the other. Both can be derived from each other. However, in the kind of grand scheme of things, especially with thinking about modern physics, then we really like those local equations. Okay, so once again, this equation here is now local in space and time. Okay, so this is an electrical field at a certain point in space, at a certain moment in time. And this field, magnetic field here, is also at that same point in space, at that same moment in time. Okay, which is why we have partial derivatives here, because technically B is a function of, X, Y, Z, and T. It's a partial derivative. Okay, so that's the statement of Faraday's law. Okay. Question? Yes. 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 E and B are really E of R and T and B of R and T. Okay? No, so this nabla operator is, yeah, so once you've chosen your coordinate system, you will represent it as a combination of purely spatial derivatives. Okay, there's no time derivative in here. But you see, your intuition is excellent because you're kind of suggesting that actually this is just, you know, space and time derivatives. Isn't it all the same thing in the end of the day in relativity? And indeed, yeah. So in relativistic notation, you can kind of write that in a more floor vector kind of way, but we're not there yet. Okay, so that's the statement here. Okay, so yeah, so that's Faraday's law. Had you even seen Faraday's law in your first course? I guess you have seen it stated, possibly as not sure. So, okay, now you have it. Okay.